Hello, my name is Hong Che, and I will introduce our paper accepted in EPPS 2021 program. First of all, thank you for reception and opportunity to present. The title is Sequential Policy Network-Based Optimal Passive Equalizer Design for an Arbitrary Channel of High Bandwidth Memory using Advantage Actor Critique. And let me start. The content for presentation is configured as introduction, previous work for research motivation, proposed our optimization methodology, verification chapter, and conclusion, finally, further works. Nowadays, high bandwidth memory has been focused as a solution of transmitting a lot of data by using 3D stacked DRAM. By stacking the DRAMs and connecting stacked DRAMs and processor using short channel in silicon interposer, high performance could be achieved. However, due to the signal integrity issues such as reflection, high frequency attenuation, and so on, such as crosstalk, the I diagram at Rx can be degraded. And as the fundamental frequency of signal increases, that issues are more severe. Therefore, some technologies are needed in order to increase the data rate without any distortion, as shown in the table about the data rate per channel with each generation. This page is about the example of passive equalization for signal integrity by using the high-pass filter. Of course, the equalization process can be achieved by diverse scheme of equalizer. But in this paper, we focused on the passive equalizer configured with the resistance and inductance. If the passive equalizer are applied to any channel, low frequency signal can be flowed to the ground. So the high frequency signal can be transmitted relatively more than our low frequency signal. As shown in the right figure, the red line with passive equalizer is more flattened than the old channel case. So the high frequency attenuation effect can be reduced. However, the parameters of passive equalizer are coupled with each other and channels parameter, so it is hard to optimize the equalizer. So some tasks for optimizing passive equalizer are needed. This is first previous work for my research motivation. This work was performed by Yasserjan and written in IEEE transactional circuits and systems. They optimized the passive equalizer in silicon interposer and could improve the eye diagram. They chose the coil shape as the passive equalizer, and the parameters such as length and width of passive equalizer were designed by grid search method. They insisted that the placement of passive equalizer is not important. However, there is a coupled relationship between passive equalizer design and placement, so I think they had to consider our design of passive equalizer. The most thing is that grid search optimization method is not reusable for a changed condition. Unless the memory channel of an HBM is fixed, engineers should repeat the grid search method for optimization. Second is also about the passive equalizer optimization method. The author, Kai-Fu, optimized the parameters of passive equalizer for the old mode impedance by using genetic algorithm. So they could flatten the differential insertion loss of channel as shown in the right figure. However, their objective function couldn't consider all signal integrity effect. And as same as first previous work, they should repeat the optimization method using genetic algorithm for unseen channel dimension. So a reusable and flexible optimization method for unseen or changed channel dimension is necessary for reducing time consumed high performance. This page shows the concept of deep reinforcement learning with neural network. This method also can be optimization method and comprise police network, action, state, and environment. Once the policy network is trained, it can suggest the optimized probability distribution for any state, as well as it can be operated in continuous space because the actor is composed of neural network. Therefore, we can sample some actions for any condition in order to optimize the objective function. That method can give us the flexibility and high performance, unlike conventional optimization method. So this is about the motivation of research. The first is coupling of design parameters and placement of passive equalizer has to be considered together. Second, eye diagram which is affected by all SI issues should be the objective function of optimization. Third, conventional optimization method should be repeated for the changed condition. Finally, deep reinforcement learning can be a solver with flexibility and improved performance for an arbitrary condition. And this page shows the overall concept of our proposed optimization method for passive equalizer design of three coupled memory channels in silicon interposer. We use the advantage actor critic algorithm for optimization. So there are two neural networks as actor and baseline critic. The actor network was configured with the sequential policy network, so actor can design passive equalizer for each memory channel. And critic network for baseline estimates the value of state that how can the eye diagram be improved by passive equalizer. Then, comparison of real reward and estimated reward transmitted to the loss function of actor network, so the actor network can be trained to increase the performance by iteration. Finally, our optimization method can suggest the probability distribution for optimal passive equalizer design in arbitrary channel condition. This is the detail of advantage actor critic algorithm. Aforementioned, there are some neural networks for action and critic as shown in the left side figure. The baseline critic network estimates the value of state. The actor decides an action at specific state. And the critic network estimates the value of action. Then the estimated values comprise the advantage function and loss function of actor network. Thus, the actor can be trained to reduce their loss function by gradient descent method. The explanation for advantage of this algorithm is described in the right side figure. For example, by using the difference between reward of action and value of state, we can reduce the training variance. Thus, we can achieve high performance of training. This page describes that the state of Markov decision process for proposed deep reinforcement learning method. Our task is design passive equalizer for arbitrary channel dimension. So the state is comprised of channel dimensions such as width and space between channels in the silicon interposer. Unlike conventional Markov decision process, our model is just one-step MDP. Therefore, there is no conversion between states. Once the action is conducted in a certain state, the episode will be end. Next page is about the action of our Markov decision process. Our policy network receives the state of channel as input, and the output comes out through the fully connected layer and GRU layer sequentially. Each output is the sub-action for design passive equalizers in each channel. Our target is 3 coupled channels in silicon interposer, so 3 sub-actions comprise the one action. Each sub-action decides the passive equalizer's parameters such as length and placement. The sub-actions are connected to each other, so co-design of passive equalizers for performance is implemented. This is our reward model for training the policy network. The reward is difference of eye height before and after an action. And mean value of eye height is targeted to increase because every eye diagram of channels is important in data tracing system. Each eye height of channel is estimated by peak distortion analysis method for simplification in order to reduce the iteration time. The peak distortion analysis method is a high estimation method using single bit response as described in mathematical expression of top right side. For verification our proposed optimization method, we use the simple shape of a line as the passive equalizer. It is embedded in silicon interposer connected to the channel in parallel. And this passive equalizer has a resistance and inductance, so it can play a role of high-pass filter. The parameters are length and placement of passive equalizer, and the range of length and placement are described in the bottom table. The range of length is from 0 mm to 5 mm with 1 mm step, and the equalizers can be located between Tx and Rx with 1 mm step. This page shows the results of our proposed method compared with the conventional optimization method, such as random search and genetic algorithm. We tested the 10 cases of channel in this silicon interposer, and we can check the result that our proposed model outperformed the other algorithms. And before designing the passive equalizer, original simulation has a closed eye diagram. Nevertheless, by using our proposed optimization method, we improved the eye height by 6.4% and 4.4% respectively in advanced design system circuit simulation. And this is the conclusion. First, proposed method outperformed conventional optimization methods such as random search and genetic algorithm for unseen channel dimension. So finally, proposed method has flexibility and high performance by using trained probability distribution for unseen dataset. And this is for the work. First thing is continuous time linear equalizer CTLE will be applied to memory channel as hybrid equalizer in order to obtain enough eye diagram and Rx, because passive equalizer is not enough to operate HBM data transmission system well. Finally, hybrid equalizer in silicon interposer will be optimized by using this optimization process, such as deep reinforcement learning with recurrent decoder. Thank you for listening.